Stroke gestures present an intuitive way to interact with software, such as through swipes on mobile devices and through application shortcuts. However, their general acceptance requires high recognition accuracy. For a recognizer to appear indistinguishable from a perfect system, accuracy must be significantly higher than 90%. Very high accuracy is possible with predefined gesture sets and robust recognizers that are trained with lots of data, but more difficult with custom gestures where only a few samples per gesture are given. Approaches based on recurrent neural networks are robust to gesture variability, allow for variable length inputs, and require no handcrafted feature extraction. Recently, deep GRU and LSTM-based networks trained on thousands of original samples performed at state-of-the-art accuracies. However, in customization scenarios, a user expects to only specify a few samples per gesture class and have no downtime before using gestures. So the two main shortcomings of RNNs prevent methods based on them from widespread adoption. They require a large amount of data to outperform alternative approaches, and they take long to train. Because RNN training time depends primarily on the training set size, the two issues are related. The more data is used for training, the higher the resulting recognition accuracy will be, but at the cost of a longer training time. Synthetic data generation methods can help solve the issue of sparse data. However, so far, efforts to synthesize gestures focused mostly on gesture realism. In this research, we focus on finding techniques that will result in the biggest accuracy boost, not the beautification of the synthesized gestures. We attempt to solve the two shortcomings through evaluating a number of synthetic data generation methods for gestures. We also introduce augmentation chaining methods, which apply complementary transformations in a specific order, and we show that this approach outperforms the alternative approaches in the literature. Finally, we show that with the right set of augmentations, used to generate synthetic training and validation sets, only a few original samples per class are required to train a highly accurate RNN gesture recognizer. For a start, we searched literature on gestures and similar time series data for data augmentation techniques. We identified a number of such techniques, and a complete list with explanations and references can be found in the paper. For the tests, we had two data pipelines, a regular pipeline and a synthetic validation pipeline, where a synthetic validation dataset double the size of the synthetic training set is also generated. The RNN model architecture used in all experiments was simple by design, because it was not the focus of our work. We used two GRU layers followed by a classification layer. The only preprocessing step that we applied translated the first point of each trajectory to the origin. This ensured that the model would be translation invariant and that it would enable classifying a single point at a time, allowing for real-time classification. Using this setup, we designed a series of 5 experiments. We tested the performance of each techniques individually, performance of their combinations. We then applied the best combination to more datasets, compared this performance against more complex alternative techniques, and explored the train time and accuracy trade-off. In the first experiment, we evaluated the performance of individual augmentation techniques. We trained a system with a single original sample per gesture class and with 300 synthetic samples generated for each of the original samples. Because there are many ways that a single original gesture per class can be sampled from the dataset, we repeated the experiment 300 times per augmentation technique and averaged the accuracies of all those runs together. We found that Gaussian noise gave the largest performance boost, followed by uniform noise and frame skipping. It's interesting that even point duplication, which occasionally inserts a copy of an existing point into the trajectory, also resulted in improved accuracy. Now that we know how each technique performs separately, we are interested in finding a set of transformations, applying which results in the best accuracy boost. This problem has a large search space, and because the order in which the techniques are chained has impact on performance, we would need to test all permutations of all combinations of 11 different techniques. This makes up over 100 million possible chains of augmentation and is impractical to test, especially when computing a fair accuracy average requires 300 model training runs. To reduce the search space of possible chains, we decided to chain together those techniques which through their transformations added variability from different categories. We first formed some simple chains that combined techniques from multiple categories, and then modified them as we observed patterns in model accuracies. We used 3 guiding principles based on our early experimentation. Using trial and error and these observations as guidance, We arrived at a chain of Gaussian noise, frame skipping, spatial resampling, perspective change, rotation, and scaling. This chain outperformed other chains that we tested, and we tested it in our next experiment, referring to it as all variability chain, or AVC. The third experiment, with the writer-dependent protocol, was designed to simulate a real-world scenario where a user specifies a single instance of a gesture class. These instances are then used to augment both the training and the validation sets, and test set consists of all the unseen data from the same user. We compared no augmentation against only Gaussian noise, against a simple augmentation chain, and our AVC chain. Gaussian noise and a simple augmentation chain served as benchmarks for the approaches generally used in the literature. We tested with 4 popular stroke gesture datasets with a single and 2 original samples per gesture class. Our AVC chain achieved the highest accuracy across all datasets. Next, we are interested in comparing our chaining approach to other more complex approaches, generally used for synthesizing realistic-looking gesture data. We used the $1 dataset and compared AVC chain to GPSR and gestures at GoGo. We found that AVC outperforms both of these alternatives. Interestingly, gestures at GoGo performed worse than the no augmentation condition in the test, and this is potentially due to the method not producing enough variability, resulting in the RNNs that were overfit. Now we know that chaining works well to improve RNN accuracy and make the user happy as a result. However, training time is another consideration in customization, because we want to reduce the user's wait time to a minimum. To measure how long the training can realistically take with AVC chain, we varied the number of synthetically generated samples per class. On a GTX 1080, training with 256 synthetic samples per class takes just under 30 seconds and results in over 96% accuracy. Our experimentation shows that chaining augmentation techniques one after another helps generate a synthetic training dataset that significantly improves RNN accuracy, as compared to the training sets of the same size where only a single augmentation technique is applied. The training time of RNNs increases with a larger training set size. Thus, instead of generating, for example, 100 samples using each augmentation technique separately, a total of 100 samples using an effective chain should be generated instead. Visual inspection of the trajectories synthesized using the AVC chain reveals that overall gesture shapes are recognizable, although the trajectories look very noisy. The impact of Gaussian noise and rotations is very pronounced, but the impact of spatial resampling is not obvious from a visual observation. Given that the presence of point count modification methods, resampling, is the main difference between the AVC chain and the simple chain, the performance gains when using the AVC chain must come from frame skipping and spatial resampling methods. Such methods are underexplored in the RNN gesture recognition literature, and based on our results, they deserve more attention and may reveal more performance gains if studied further. Our work has some limitations. We did not explore different model sizes and architectures. Even though this was not the focus of our work, additional performance boosts may be uncovered by investigating in this direction. We also only worked with single-stroke 2-dimensional gestures, and in the future we plan to extend the chaining steps to 3D gestures, skeletal data, and also multi-stroke gestures. Another interesting possibility to reduce the need for large datasets and long training time is to use transfer learning to perform fine-tuning on user-specified dataset. In conclusion, we showed that applying the right augmentation steps greatly increases gesture recognition accuracy for RNNs, even in sparse data scenarios. Please refer to our paper for more details about this work, and you can find the reference implementation for the augmentation techniques in our code repository.